Welcome back to PowMr channel. In this video, we will continue our series on common mistakes in PV system setup. This is the third video in the series, so if you haven't watched the previous two episodes yet, feel free to click the link in the description below to check them out. Avoiding these often overlooked mistakes can help prevent unnecessary losses and system failures. Now let's dive into the main topic of this video. Mistake 1. Overrated charge or discharge current settings for solar charge controllers and all-in-one inverters. When setting the charge and discharge current for connected batteries, users should pay close attention to following three factors: the maximum charge or discharge current supported by the battery itself, the overcurrent protection threshold of the BMS, the potential for transient current exceeding the set value during system operation. If the configured current exceeds the BMS's current handling capability, it can lead to several consequences such as overheating and failure of MOSFETs, excessive power loss in the shunt resistor causing it to burn out, or even damage to the internal protection circuits of the main control due to current surges, ultimately resulting in BMS failure. To ensure stable system operation, it is recommended to set the charge or discharge current to 80% to 90% of the BMS's maximum rated current, while also staying within the battery's rated specifications. For example, with a 100 amp-hour lithium iron phosphate battery, whose BMS has a discharge protection threshold of 120 ampere, the discharge current should be set between 90 ampere and 100 ampere to leave a safe margin. Proper current settings not only ensure safe battery operation but also help extend the overall lifespan of the system. Mistake 2. Oversized PV array voltage. The configuration of the PV array is a crucial part of PV system design. It directly impacts the system safety, efficiency, power generation performance, and equipment lifespan. If the open circuit voltage of the PV array exceeds the inverter or charge controller's maximum input voltage, the high voltage may instantly damage key components such as the MOSFETs, capacitors, or driver chips at input stage. Furthermore, damage caused by input voltages exceeding the rated limit is considered a user-induced fault and is not covered by warranty. Users will need to cover any repaired or replacement costs themselves. To avoid this, PV array design must be based on the actual specifications of the PV modules and inverter or controller. Ensure that the total open circuit voltage of the serial connected module stay within the device's maximum input voltage. The operating voltage falls within the MPPT range. The combined current in power connections does not exceed the device's input current limit, and the total input power does not exceed the device's maximum power capacity. Mistake 3. Battery charge or discharge current does not match inverter or system requirements. When configuring energy storage for an inverter system, it's essential not only to match the system voltage and ensure battery type compatibility, but also to verify that battery's maximum charge and discharge current meets the inverter's power demands. For example, imagine setting up a 10 kW off-grid inverter with a 48-volt system voltage and pairing it with a 200 amp-hour lithium iron phosphate battery that supports a maximum continuous charge or discharge current of 100 ampere. This setup introduces multiple issues. Under weak sunlight or at night, the battery cannot supply enough current to support a 10 kW load. The battery's maximum output power is only 48 volt times 100 ampere equals 4.8 kW, well below the inverter's full load capacity. The inverter may frequently trigger overload protection or fail to match load demands. During sunny periods with high solar generation, the inverter's MPPT can provide up to 200 ampere charging current, but the battery's limit of 100 ampere means much of the solar energy goes unused, resulting in lower charging efficiency. So, even though the battery capacity appears efficient, its current handling ability falls short, making it unable to support the inverter's rated power and negatively affect the system's performance and user experience. To prevent this, the battery's continuous charge or discharge current should exceed the inverter's rated operating current by 10% to 20%, providing a safe operating margin and ensuring system stability. Mistake 4. Wi-Fi frequency band mismatch during inverter configuration. Some users experience persistent issues when trying to connect the inverter's Wi-Fi module to a router. In most cases, the root cause is a frequency band mismatch. Most Wi-Fi modules used in solar inverters, such as those based on ESP826s, ESP32, or RTL series chips, support only the 2.4 GHz band. They do not support 5 GHz Wi-Fi, which is often used in modern routers. Additionally, in certain situations, inverters are installed in garages, outdoor locations, or areas with limited human activity. The 2.4 GHz signal has a better wall penetration and a longer range compared to 5 GHz, making it more suitable for stable communication in challenging environments. For a system design perspective, 2.4 GHz module also consume less power, which helps reduce the inverter's overall standby power consumption, making them ideal for long-term, energy-efficient operation. To make the setup go smoothly, make sure your router has the 2.4 GHz band enabled. If your router combines the 2.4 GHz and 5 GHz signals under one NAM, try splitting them into two separate NAMs. This makes it easier for the inverter to connect to the right one. Mistake 5. Inconsistent firmware versions prevent successful inverter power communication. When setting up multiple inverters in parallel configuration, some users, despite correctly wiring and configuring the system, still encounter power communication failures. The most common cause of this issue is inconsistent firmware versions across the inverters. Parallel operation requires multiple inverters to synchronize and share key operating parameters such as phase, output voltage, and current distribution. If the inverters are running different firmware versions, they may use incompatible communication protocols, control logic, or internal functions, preventing successful communication. Before you set up the power system, double check that all inverters are using the same firmware. You can find the version info on the screen or Vista app. If they are not the same, update them first. We've got tutorial video you can follow for that. Once the firmware versions are unified, the power system can be reconfigured and should operate reliably. That concludes the third part of our series on common PV system setup mistakes. We hope this video has been helpful. Feel free to share your own setup experience or questions in the comment section below. Thanks for watching, and we will see you in the next video.